In 1968, believe it or not, engineers tested asphalt by chewing it. Literally, they would bite into a chunk of binder to judge its flexibility. No sensors, no simulations, just instinct and experience. Now, in 2025, things couldn't be more different. We use smart machines, temperature sensors, even AI to check how asphalt will perform over time in heat, cold, or heavy traffic. In just 50 years, we have gone from chewing tar to building roads that can heal themselves, charge electric vehicles, and even warn us before they crack. So, how did we get here? What changed? Let's take a look at how asphalt went from a simple black mix to one of the most advanced materials in modern construction. Look around. Chances are the road beneath your feet is made of asphalt. In fact, over 94% of paved roads in the United States are surfaced with asphalt. It's the material that connects cities, carries our freight, supports emergency response, and underpins the global economy. But behind the scenes, the story of asphalt is anything but ordinary. It's a timeline of experiments, failures, redesigns, and eventually breakthroughs. Especially in the last few decades, the pace of advancement has been nothing short of revolutionary. Let's rewind to the 1970s. Highways were cracking faster than expected. Pavements were rotting, fatiguing, and disintegrating under temperature extremes. Repairs were constant. Road closures became common. Public confidence in infrastructure was dropping. And all of this happened against the backdrop of an energy crisis and rising oil prices, pushing the cost of asphalt production even higher. It was clear the old ways of designing roads were no longer sustainable. That was the turning point, and from this urgency came the Strategic Highway Research Program, or SHRP. The SHRP initiative brought together federal agencies, state DOTs, researchers, and industry experts. Their mission was to understand why do pavements fail and how can we design mixes that don't. This gave rise to one of the most impactful contributions to the pavement science: performance-graded binders. Before SHRP, we used either penetration or viscosity grades to classify asphalt. But those tests couldn't account for how asphalt behaves in real service conditions during scorching summers, freezing winters, or under heavy loads. Performance-graded binders, or PG binders, solve this. These binders are classified not by how thick they are in a lab, but by the temperature range they are expected to endure in the field. For example, a PG6422 binder is designed for high service temperature up to 64 degrees Celsius and low temperature down to -22 degrees Celsius. This allowed engineers to match binders to the climate zone and traffic demands of a specific region, replacing guesswork with data. But changing the binder wasn't enough. Mix design, the way we blend aggregates, asphalt, and air, also had to evolve. For decades, engineers used the Marshall mix method, which relied on compacting samples with a hammer and checking for basic stability. It worked during the period, but it couldn't predict performance under real-world traffic conditions. Then comes SuperPave, short for Superior Performing Asphalt Pavements, changed all these. It introduced volumetric design, performance modeling, and aggregate optimization. The focus shifted to voids in mineral aggregate, VMA, air voids, and the gradation curves, ensuring mixes weren't just stiff enough, but also flexible and fatigue resistant. But one lesson became clear. Roads don't fail just because they are weak. They also fail when they are too strong. Too much stiffness leads to thermal and fatigue cracking. Too much flexibility leads to rutting and permanent deformation. So came the idea of balanced mix design, BMT. This approach combines volumetric design with performance testing using methods like the Hamburg wheel tracker to test rutting resistance and the indirect tensile strength test to check for cracking. The goal is to design a mix that can resist both forms of failure, achieving a true balance between durability and resilience. Once the performance improved, attention turned to sustainability. Traditional hot mix asphalt HMA requires high temperature around 150 to 180 degrees Celsius to make it workable. That consumes fuel and emits greenhouse gases. Entering the innovation of warm mix asphalt WMA by adding chemical or organic additives or using formed asphalt technology. WMA can be produced at 20 to 40 degrees Celsius lower than HMA without sacrificing performance. And that's what we need. This cuts fuel consumption, reduces plant emissions, and makes compaction easier, especially useful in remote areas or cold climates. Simultaneously, the use of reclaimed asphalt pavement RAP increased dramatically. RAP contains both aged binder and high-quality aggregates, and by 2025, nearly 90% of RAP generated in road work is reused, making asphalt one of the most recycled materials on the planet. Even recycled plastic waste is being trialed in new formulations, reducing landfill burdens while enhancing binder performance in some use cases. Highway engineers then asked a radical question. Instead of building roads to last 10 to 15 years, can we build them to last 50? And that's the concept behind Perpetual Pavement, a layered design where only the surface cores wears out. The intermediate and the base layers are designed to remain flexible, fatigue resistant, and undisturbed over multiple surface renewals. This approach minimizes life cycle cost and limits future reconstruction, reducing lane closures, waste generation, and user disruption. But mixed design is only half the story. Execution matters. Inconsistent compaction or poor placement can ruin even the best material. Today's construction sites are equipped with intelligent compaction systems. Rollers are now fitted with GPS and real-time stiffness sensors. They map out compaction patterns on site, ensuring uniform density across every pass. Meanwhile, 3D laser guidance and GPS-controlled pavers lay asphalt to centimeter-level precision, minimizing overuse of material and guaranteeing smoother ride quality. To validate designs, we no longer rely solely on simulations. Facilities like MN Road in Minnesota and NC80 in Alabama replicate years of traffic loading in just months. Real trucks drive over these test sections while sensors monitor the strain, temperature, moisture, and surface performance, helping us identify the best material and strategies for different environments. And now we step into a new phase, the era of 2025. The asphalt of today is no longer passive. It's smart, it's adaptive, and it's responsive. Self-healing asphalt is being trialed, with microcapsules embedded inside the binder that release healing agents when cracks form. In field test, these systems extend pavement life by 30% or more, reducing maintenance cycles. Inductive charging pavements are also being piloted, using embedded coils to wirelessly recharge electric vehicles as they drive, opening the door for electric highways for the future. Cities are deploying cool pavement coatings to reduce surface temperatures by up to 5 degrees Celsius, addressing the urban heat island effect, especially in warm climates. And under the surface, Neoloy Geocells are reinforcing base layers. reducing the need for thick aggregate layers and making construction more sustainable on poor soils. Maintenance has shifted from reactive to predictive. AI models now process pavement data from drones, satellites, and the embedded sensors to estimate the pavement condition index (PCI) values in real time. Ground penetrating radar (GPR) is used to assess layer thickness and moisture conditions with sub 2% error, enabling surgical repairs without full reconstruction. The industry is also aligning with climate goals. National agencies have released decarbonization roadmaps for asphalt, calling for bio-based binders, electrified paving equipment, and low-carbon additives. This isn't optional, it's the next frontier. We have come a long way in designing roads that last, but when materials fail or maintenance falls behind, the cracks still show. And while new tech is promising, it takes time to scale across every street and highway. And that's why potholes aren't going away just yet, and knowing how to fix them still matter. So if you are curious how the pros do it, from quick patches to a full depth repair, check out our video on pothole repair.